then crest coincides with trough in mutually destructive cancellation, and one gets a band of darkness. Thus, the appearance of interference patterns of alternating light and dark is an unmistakable signature of the presence of waves. Young's observations appeared to have settled the matter. Light is wave-like. As the 19th century proceeded, the nature of the wave motion associated with light seemed to become clear. Important discoveries by Hans Christian Ørsted and by Michael Faraday showed that electricity and magnetism, phenomena that at first sight seemed very different in their characters, were, in fact, intimately linked with each other. The way in which they could be combined to give a consistent theory of electromagnetism was eventually determined by James Clerk Maxwell, a man of such genius that he can fittingly be spoken of in the same breath as Isaac Newton himself. Maxwell's celebrated equations, still the fundamental basis of electromagnetic theory, were set out in 1873 in his Treatise on Electricity and Magnetism, one of the all-time classics of scientific publishing. Maxwell realized that these equations possessed wave-like solutions, and that the velocity of these waves was determined in terms of known physical constants. This turned out to be the known velocity of light. This discovery has been regarded as the greatest triumph of 19th century physics. The fact that light was electromagnetic waves seemed as firmly established as it could possibly be. Maxwell and his contemporaries regarded these waves as being oscillations in an all-pervading elastic medium, which came to be called ether. In an encyclopedia article, he was to say that the ether was the best confirmed entity in the whole of physical theory. We call the physics of Newton and Maxwell classical physics. By the end of the 19th century, it had become an imposing theoretical edifice. It was scarcely surprising that grand old men like Lord Kelvin came to think that all the big ideas of physics were now known, and all that remained to do was tidy up the details with increased accuracy. In the last quarter of the century, a young man in Germany contemplating an academic career was warned against going into physics. It would be better to look elsewhere, for physics was at the end of the road, with so little really worthwhile left to do. The young man's name was Max Planck, and fortunately, he ignored the advice he had been given. As a matter of fact, some cracks had already begun to show in the splendid facade of classical physics. In the 1880s, the Americans Michelson and Morley had done some clever experiments intended to demonstrate the Earth's motion through the ether. The idea was that if light was indeed waves in this medium, then its measured speed should depend upon how the observer was moving with respect to the ether. Think about waves on the sea. Their apparent velocity as observed from a ship depends upon whether the vessel is moving with the waves or against them, appearing less in the former case than in the latter. The experiment was designed to compare the speed of light in two mutually perpendicular directions. Only if the Earth were coincidentally at rest with respect to the ether at the time at which the measurements were made would the two speeds be expected to be the same. And this possibility could be excluded by repeating the experiment a few months later, when the Earth would be moving in a different direction in its orbit. In fact, Michelson and Morley could detect no difference in velocity. Resolution of this problem would require Einstein's special theory of relativity, which dispensed with an ether altogether. That great discovery is not the concern of our present story, though one should note that relativity, highly significant and surprising as it was, did not abolish the qualities of clarity and determinism that classical physics possessed. That is why, in the preface, I asserted that special relativity required much less by way of radical rethinking than quantum theory was to demand. Spectra.